Every few milliseconds, something in deep space screams, not in sound, but in radio waves so intense they release more energy in a single flash than our sun produces in an entire year. Scientists have now catalogued thousands of these bursts. They have pinpointed the galaxies they come from. They have built continent-spanning telescope arrays to catch them in the act. And yet, after nearly 2 decades of study, some of these signals still resist clean explanation. Not because science is failing, but because the universe's most extreme objects often announce themselves through emissions that arrive long before any full physical understanding can follow. This is not about aliens. This is about what happens when the cosmos sends you a signal and dares you to decode it. If you enjoy journeys into the frontiers of what science still cannot fully explain, hit that like button and subscribe. It helps more than you think, and I genuinely appreciate every one of you. Now, let's begin. Deep space does not introduce itself through photographs. It does not send polite invitations or wait for our telescopes to be ready. The most extreme environments in the universe make themselves known in a different way entirely. They send signals. Brief, violent, and impossibly energetic flashes of electromagnetic radiation that cross billions of light years before arriving at our instruments, often from objects we have never seen, cannot image, and in some cases still cannot classify. Everything we know about the strangest objects in the cosmos began not with a picture, but with a detection. A spike on a screen, a pattern in the data, a signal that should not exist based on what we thought we understood. And the most unsettling truth about modern astrophysics is not that these signals have stopped arriving. It is that they keep arriving, in growing numbers, with increasing clarity, and some of them still resist clean explanation even after thousands of detections and years of study. This is not a story about aliens. This is not about conspiracy or paranormal mystery. This is about what happens when the universe's most violent phenomena announce themselves through emissions that our instruments can record, but our theories cannot yet fully decode. The journey begins with a single burst that almost no one noticed when it actually happened. In 2001, the Parkes Radio Telescope in New South Wales, Australia, recorded a peculiar flash of radio energy during a routine pulsar survey. The data was archived. Nobody looked at it closely. The burst sat buried in magnetic tape storage for 6 years before anyone realized what it contained. In 2007, a team led by Duncan Lorimer, along with Matthew Bales, Maura McLaughlin, and undergraduate student David Narkevich, was sifting through that archived Parkes data when they found something extraordinary, a single pulse of radio emission lasting less than 5 milliseconds, enormously bright, and unmistakably originating from far outside the Milky Way. The signal displayed a property called dispersion, a frequency-dependent time delay caused by the pulse passing through ionized gas between its source and our telescope. Higher frequency components of the signal arrived fractionally earlier than lower frequency components. The amount of this delay, quantified as the dispersion measure, told the researchers something stunning. This burst had travelled through so much intervening material that it must have originated at cosmological distances, hundreds of millions or even billions of light years away. A single millisecond flash from across a significant fraction of the observable universe. The energy required to produce such a signal at that distance was staggering. In less than 5,000ths of a second, whatever produced this burst released as much energy in radio waves as our sun produces over days or weeks. The Lorimer Burst, as it came to be known, was the first confirmed fast radio burst, and it opened a door that astrophysics has been struggling to walk through ever since. The immediate reaction was cautious excitement followed by deep skepticism. One burst, from one telescope, found in archival data years after the fact. It could have been interference. It could have been an instrumental artifact. Radio telescopes are sensitive machines that can pick up signals from microwave ovens, passing satellites, and electrical faults in their own wiring. The astronomy community needed more examples before it would take this seriously. Those examples came slowly at first. By 2013, a team led by Dan Thornton published 4 additional fast radio bursts from the Parkes telescope, confirming that the Lorimer Burst was not a one-time anomaly. These new detections shared the same hallmarks: millisecond durations, enormous dispersion measures indicating extragalactic origin, broadband radio emissions sweeping across a wide range of frequencies. The signals were real. They were coming from deep space, and nobody had a convincing explanation for what produced them. But the path from skepticism to acceptance was not smooth, and one particular episode nearly derailed the field entirely. Throughout the early years of fast radio burst research, Parkes telescope data also contained a separate class of signals called peritons, named after a mythological winged deer from medieval bestiaries. These signals looked superficially similar to fast radio bursts. They showed the same kind of frequency-dependent sweep across the telescope's detection band. They arrived as brief, bright pulses. To a casual eye, they could easily be mistaken for genuine cosmic signals, and for several years, they muddied the waters considerably. Some researchers worried that fast radio bursts themselves might be nothing more than a variant of these terrestrial contaminants, elaborate instrumental artifacts dressed up in the appearance of cosmic origin. The mystery of the peritons was solved in 2015 by Emily Petroff and colleagues at Swinburne University. Through meticulous analysis of the signal's properties and arrival patterns, the team traced the peritons to their source. They were being produced by microwave ovens in the Parkes Observatory's kitchen and visitor facility. When a microwave oven door was opened before the heating cycle had fully completed, the magnetron inside the oven emitted a brief burst of radio frequency radiation that the telescope's sensitive receivers picked up. The frequency sweep of these microwave bursts mimicked the dispersion signature of a genuine cosmic signal, creating a deceptive resemblance to fast radio bursts. The timing patterns confirmed it. Peritons clustered around lunchtime. The universe does not observe lunch breaks, but observatory staff do. The resolution of the periton mystery was crucial for two reasons. First, it eliminated a major source of contamination from the data, allowing researchers to confidently separate genuine fast radio bursts from terrestrial interference. Second, and more importantly, it demonstrated exactly how rigorous the vetting process for these signals had to be. Radio astronomy operates in an environment saturated with human-made radio frequency interference. Mobile phone towers, satellites, aircraft radar, electrical equipment, even car ignition systems can produce radio signals that contaminate telescope data. Distinguishing a genuine millisecond pulse from a galaxy billions of light-years away from a stray emission produced by kitchen equipment a few hundred meters from the telescope requires extraordinary care. The fact that the periton contamination was identified and eliminated gave the research community far greater confidence that the remaining fast radio burst detections were real. The signals that survived this scrutiny were genuinely cosmic in origin. Their dispersion measures exceeded anything that local interference could produce. Their sky positions were consistent with extragalactic sources. Their properties matched theoretical predictions for signals traveling through the intergalactic medium. The microwave oven episode, embarrassing as it initially seemed, ultimately strengthened the field by forcing a level of rigor that made subsequent discoveries far more credible. Understanding why these surviving signals are so puzzling requires understanding what they physically are. A fast radio burst is a transient pulse of coherent radio emission. Coherent means the radio waves are organized rather than random, implying that whatever generates them involves a mechanism that forces enormous numbers of charged particles to radiate in lockstep. This is not thermal radiation, not the gentle glow of a hot object. This is something more like a cosmic laser operating at radio wavelengths. The bursts are unresolved, meaning they appear as point sources even to the most sensitive instruments. They are broadband, spanning a wide range of radio frequencies, typically between 400 MHz and 8 GHz depending on which telescope detects them. And they are fast. Most last between a fraction of a millisecond and a few milliseconds. Some show internal structure, with multiple subbursts nested within the main pulse, each drifting downward in frequency over time. The brevity of the bursts constrains the size of the emitting region. Because nothing can communicate information faster than light, an object that varies on a timescale of 1 millisecond must be smaller than the distance light travels in 1 millisecond, roughly 300 kilometers. Whatever produces these bursts is compact, extraordinarily compact, the size of a small asteroid producing energy outputs that rival entire galaxies for that fleeting instant. The dispersion measure became the first great tool for understanding these signals. As a fast radio burst travels through the cosmos, it passes through the ionized gas that fills the space between galaxies. This gas, known as the intergalactic medium and the interstellar medium of any galaxies along the line of sight, slows lower frequency radio waves slightly more than higher frequency waves. The result is a characteristic sweep in the signal. When astronomers plot the burst across frequency and time, they see a distinctive downward curve, with the highest frequencies arriving first and the lowest frequencies trailing behind. The total amount of this delay, the dispersion measure, is directly proportional to the total column of free electrons between the source and the telescope. For sources within our galaxy, like ordinary pulsars, dispersion measures are modest, typically a few tens to a few hundred units. The Lorimer Burst had a dispersion measure of 375, far exceeding what any galactic source could account for. The excess dispersion had to come from electrons in intergalactic space, placing the source at a distance of roughly 1.5 billion light-years. Subsequent fast radio bursts displayed even higher dispersion measures, some exceeding 2,000, implying sources at distances of billions of light-years. The dispersion measure gave astronomers a rough cosmic yardstick, but it also introduced a new problem. Knowing how far away a signal comes from is not the same as knowing what produced it. Distance tells you the energy budget. It tells you the signal travelled through a certain amount of ionized material. It does not tell you what kind of object screamed across the universe in less time than it takes a hummingbird to beat its wings. By 2015, the field had a growing catalogue of fast radio bursts, all of them one-off events. Each source had flashed once and never been seen to flash again. This raised a fundamental question that shaped the theoretical landscape for years. Were fast radio bursts produced by cataclysmic events, one-time explosions or collisions that destroyed the source in the process of creating the signal? If so, each burst was a death cry, the final emission from an object that no longer existed. Models proliferated along these lines: colliding neutron stars, evaporating black holes, collapsing magnetic fields. Each model had the convenient property that it naturally explained why bursts did not repeat. The source was gone. There was nothing left to produce a second signal. Then, in 2016, everything changed. A team led by Laura Spittler and Paul Schultz, using the massive RAC-BO radio telescope in Puerto Rico, announced that one fast radio burst source had produced multiple bursts. The source, originally detected by RAC-BO in 2012, had been observed to flash again, and again, and again. Over the course of dedicated follow-up observations, the telescope recorded 10 distinct bursts from the same sky position, each with the same dispersion measure, confirming they all originated from the same object at the same distance. The source was not dead. It was alive, active, and repeating on an irregular schedule. This single discovery split the field in two. Every cataclysmic model that required the source to be destroyed in the act of producing the burst was immediately ruled out for this particular object. You cannot have a repeating signal from something that blew itself apart. Whatever produced these bursts had to survive the emission process intact, retaining enough energy and structural integrity to burst again days, weeks, or months later. The discovery did not eliminate cataclysmic models entirely. It was still possible that non-repeating bursts came from destructive events while repeating bursts came from something else. But it proved that at least one class of fast radio burst source was a persistent engine, not a one-time explosion. And it opened the door to a question that remains unresolved to this day. Are all fast radio bursts fundamentally the same phenomenon, with repetition simply depending on how long and how carefully we monitor a given source? Or do repeating and non-repeating bursts genuinely come from different types of objects, produced through different physical mechanisms, united only by their superficial similarity in a radio telescope? The RAC-BO discovery had another immediate consequence. Because the source was repeating, astronomers could plan observations in advance rather than relying on lucky catches. They could point multiple telescopes at the known position and wait for the next burst. This made it possible, for the first time, to localize a fast radio burst to a specific host galaxy using interferometric techniques, a story that would unfold over the following year and that would add yet another layer of complexity to the mystery. But the conceptual shift mattered as much as the practical one. The existence of a repeating source proved that fast radio burst engines could be long-lived, that they could turn on and off repeatedly, and that the phenomenon was not necessarily tied to the destruction of the emitting object. This opened the theoretical space for models involving magnetars, pulsars with extreme properties, and compact objects in binary systems, all of which could in principle produce repeated bursts over extended periods. The field after 2016 was fundamentally different from the field before it. Fast radio bursts were no longer just mysterious flashes. They were mysterious flashes from sources that sometimes persisted, sources that could be studied over time, sources whose behavior could be tracked and compared from burst to burst. The mystery had acquired a temporal dimension that made it simultaneously more tractable and more perplexing. The field accelerated dramatically when new telescopes came online. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, began detecting fast radio bursts in 2018, and it transformed the field almost overnight. CHIME is not a traditional dish telescope. It consists of 4 massive cylindrical reflectors in British Columbia, Canada, with no moving parts. It stares at the entire overhead sky every single day, monitoring a broad swath of radio frequencies between 400 and 800 MHz. This design makes it an extraordinarily efficient fast radio burst detection machine. Where Parkes might catch a handful of bursts per year, CHIME detects 2 to 3 per day. By the time the CHIME collaboration released its second catalogue in 2025, it had recorded over 4,500 fast radio bursts. This represents a nearly 10-fold increase from the 536 events in the first catalogue. Among those, 3,564 appeared to be one-off events, single bursts never seen to repeat from the same location. 981 additional bursts came from 83 sources that had been observed to repeat. This flood of data should have solved the mystery. In many areas of science, going from a handful of observations to thousands is enough to reveal the underlying pattern. But fast radio bursts refused to cooperate. The data revealed not a single clean answer, but a web of new questions that made the original mystery deeper and more textured than anyone anticipated. The most fundamental question is deceptively simple. What is the difference between a fast radio burst that repeats and one that does not? At first glance, this seems like it should be straightforward. Either a source produces multiple bursts, or it produces only one. But the reality is far more complicated. Observational limitations make it impossible to confirm that any source is truly non-repeating. A telescope can only monitor a given patch of sky for a limited time. A burst source might repeat once every few years, or once every few decades, and our current observation windows would miss it entirely. Some sources classified as non-repeating in the first CHIME catalogue were later found to be repeaters when additional bursts arrived during extended monitoring. Machine learning algorithms applied to the CHIME data suggest that a significant fraction of apparently non-repeating bursts may actually be hidden repeaters whose subsequent emissions were simply too faint or too infrequent to catch. This classification uncertainty is not a minor bookkeeping problem. It goes to the heart of what produces these signals. If all fast radio bursts come from the same type of source, then the distinction between repeating and non-repeating is purely observational, an artifact of our limited monitoring time and sensitivity. If, however, repeating and non-repeating bursts come from genuinely different physical mechanisms, then the universe contains at least 2 distinct classes of phenomenon that produce signals we currently lump under the same name. The evidence leans toward genuine diversity. Repeating fast radio bursts tend to show broader pulses in time and narrower bandwidths in frequency compared to non-repeaters. Their sub-burst structures drift downward in frequency in ways that one-off bursts typically do not. Statistical analyses of burst morphology suggest at least 2 populations and possibly more. Some researchers have identified as many as 5 distinct subgroups within the CHIME data using unsupervised clustering algorithms. The implications are profound. We may not be dealing with a single mystery, but with an entire family of mysteries wearing the same disguise. The challenge deepens when you consider what localization has and has not revealed. In the early years, fast radio bursts could not be precisely located because single-dish telescopes like Parkes have poor angular resolution. A burst might come from a general direction in the sky, but pinning it to a specific galaxy was impossible. This changed with the development of interferometric techniques, using multiple telescopes spread across large distances to triangulate burst positions with precision measured in fractions of an arcsecond. The first fast radio burst localized to a specific host galaxy was the repeater FRB 2001-21-10-2A in 2017. Researchers pinpointed it to a small, low-metallicity dwarf galaxy, approximately 3 billion light-years away, embedded in a region of intense star formation near a persistent compact radio source. The environment looked exactly like what you might expect if the burst came from a young magnetar born in a recent supernova. This seemed like progress, but subsequent localizations muddied the picture rather than clarifying it. Other fast radio bursts were traced to massive spiral galaxies, to the outskirts of elliptical galaxies, to regions with no obvious young stellar population, and even to globular cluster environments where stars are ancient and no recent supernova activity should be occurring. If all fast radio bursts came from young magnetars born in supernovae, they should preferentially inhabit star-forming regions. Many do, but some do not. And the ones that do not are exactly the ones that challenge every simple model. This is where a critical distinction becomes essential. Detection, localization, classification, and explanation are 4 separate stages of understanding, and confusing them creates the illusion that science either knows everything or knows nothing. Detection means recording the signal. Astronomers have become extremely good at this. CHIME alone catches fast radio bursts daily, and new instruments like the Deep Synoptic Array and the Square Kilometre Array Pathfinder telescopes are adding detections at accelerating rates. Localization means determining where the signal came from with enough precision to identify a host galaxy and sometimes a specific region within that galaxy. This capability has improved dramatically with the completion of the CHIME Outrigger Array in 2025, which uses telescopes spanning from British Columbia to West Virginia to achieve pinpoint accuracy through very long baseline interferometry. Classification means determining what category the signal belongs to. Is it a repeater or a non-repeater? Is it associated with a magnetar, a neutron star merger, a binary interaction, or something else? This is where the process begins to struggle. The categories are blurry, the boundaries are uncertain. Signals that look identical on first detection can turn out to have completely different origins when studied further. An explanation means identifying the specific physical mechanism that produces the emission. This is the stage where modern astrophysics hits a wall. We can detect thousands of fast radio bursts. We can localize dozens to specific galaxies. We can tentatively classify many into broad categories. But we cannot yet explain, with a single unified physical model, how the emission is actually generated, why it varies so dramatically from source to source, or why some of the most energetic bursts in the universe come from environments that seem incompatible with each other. The gap between detection and explanation is not a failure. It is the signature of frontier science encountering phenomena that are genuinely new. Pulsars were detected in 1967 and immediately classified as potential alien signals before being recognized as rotating neutron stars. Gamma-ray bursts were detected in the late 1960s by military satellites designed to monitor nuclear weapons tests, and their origin remained debated for decades. In both cases, the signals arrived first. The understanding came later, sometimes much later. Fast radio bursts appear to be following the same pattern, but with an added layer of complexity that neither pulsars nor gamma-ray bursts presented. The sheer diversity of fast radio burst properties, the range of host environments, the mixture of repeating and apparently non-repeating behavior, and the extreme energies involved all suggest that the universe may be producing these signals through multiple channels rather than one, and that possibility means the explanation, when it finally comes, may not be a single answer, but a family of answers tied to the most extreme objects and events the cosmos can create. This pattern, signals arriving ahead of understanding, is not unique to fast radio bursts. It is how the universe has always revealed its most extreme inhabitants. Black holes were predicted mathematically before any observational evidence existed, but the first X-ray signals from what we now know are black hole accretion disks arrived decades before anyone could confirm what they meant. Neutron stars were proposed as theoretical curiosities in the 1930s, but the pulsing radio signals that revealed their existence did not arrive until 1967, and even then, the initial interpretation was wrong. Gravitational waves were predicted by Einstein in 1916, but the first confirmed detection from a pair of merging black holes did not come until 2015, nearly a century later. In each case, the universe was broadcasting information about extreme objects long before humanity had the theoretical framework to decode those broadcasts. The signals were always there. The understanding had to catch up. Fast radio bursts represent the current frontier of this pattern. They are signals from objects and environments so extreme that existing theories can partially describe them, but cannot yet fully account for their behavior. The dispersion measures prove they come from cosmological distances. The energies prove they involve compact objects with extraordinary power outputs. The millisecond timescales prove the emitting regions are smaller than most asteroids. The polarization properties prove the magnetic fields involved are intense and highly organized. Every measurable property points toward extreme compact objects, likely involving neutron stars or similar remnants, operating under conditions that push known physics to its limits. But the specific mechanism, the exact chain of events that converts magnetic energy, or rotational energy, or gravitational energy into a coherent millisecond flash of radio emission detectable across billions of light years, remains an open question with dozens of competing models and no single consensus. What makes this moment in the history of fast radio burst science particularly remarkable is the pace of discovery. In 2007, the field had one burst. By 2013, it had a handful. By 2016, it had its first repeater. By 2018, CHIME began flooding the catalogues with hundreds per year. By 2025, the total exceeded 4,500, with precise localizations available for a growing fraction. The observational machinery is now far ahead of theoretical understanding. We are collecting these signals faster than we can explain them, and the instruments are only getting more powerful. The CHIME outrigger array, the deep synoptic array, the 500-meter aperture spherical telescope known as FAST in China, and the upcoming square-kilometer array will continue increasing both the detection rate and the precision with which each burst can be located and characterized. The data is not slowing down. If anything, it is accelerating, which means the gap between what we can detect and what we can explain is likely to grow before it shrinks. This is the reality that defines everything about these signals. Deep space does not wait for our theories to be ready. It sends its most extreme phenomena to our doorstep in the form of signals, brief and blinding, that carry information about objects and environments we have barely begun to understand. The universe broadcasts first and explains never. The explaining is our job, and the most important signals arriving right now are the ones where that job is not yet done. The fast radio bursts catalogued by the thousands are just the beginning of a much stranger story, because they are not the only class of mysterious signal-defying explanation. There is another category of deep space emission that repeats on timescales no known object should be capable of producing, signals so slow and so regular that they broke the models the moment they were discovered. And those signals are coming from much closer to home. On March 16th, 2025, the CHIME radio telescope in British Columbia recorded a fast radio burst that would earn a nickname usually reserved for once-in-a-generation astronomical events. The signal, formally designated FRB 2025-0316A, arrived from the direction of the Big Dipper. It lasted less than a millisecond, and in that sliver of time, it released more energy in radio waves than our Sun produces in 4 days. The burst was not merely bright, it was the brightest fast radio burst ever recorded, earning the nickname RBFLOAT, short for Radio Brightest Flash of all time. What made RBFLOAT historic was not just its intensity, but what happened next. Or more precisely, what did not happen next. Because despite being the most luminous fast radio burst in the history of the field, and despite originating from a galaxy close enough to study in extraordinary detail, RBFLOAT has never repeated. Not once. And this silence, from the loudest signal ever caught, is one of the most confounding facts in modern radio astronomy. The detection of RBFLOAT coincided with a major upgrade to the CHIME Observatory. 3 smaller outrigger telescopes, positioned in British Columbia, Northern California, and West Virginia, had just come fully online. These outriggers worked together with the main CHIME array, using a technique called very long baseline interferometry, combining signals from telescopes separated by thousands of kilometers to achieve pinpoint angular resolution. The result was extraordinary. Astronomers localized RBFLOAT to a patch of sky only about 45 light-years across at the source distance. To put that precision in perspective, it is like identifying a single guitar pick from 1,000 kilometers away. That localization placed the burst squarely within a spiral arm of NGC 4141, a barred spiral galaxy approximately 130 million light-years from Earth. This is remarkably close by fast radio burst standards. Most detected bursts originate from distances of billions of light-years. RBFLOAT came from practically next door, cosmically speaking, which made its brightness even more astonishing. A burst this luminous from a relatively nearby galaxy suggested an energy output at the extreme upper end of what any known compact object should be capable of producing in radio wavelengths. The follow-up campaign was immediate and aggressive. Within days, the James Webb Space Telescope turned its infrared instruments toward the precise location within NGC 4141, where the burst had originated. Webb detected a faint infrared source at the burst position, designated NIR1, that had not been catalogued before. Whether this infrared source is physically associated with the fast radio burst or merely a chance alignment remains uncertain, but if the association is real, it could represent the first detection of a fast radio burst counterpart at infrared wavelengths. Ground-based observatories also joined the effort. The Keck Cosmic Web Imager revealed that RBFLOAT originated from a star-forming region hosting massive stars. This environment is consistent with what you might expect if the burst came from a young magnetar or a recently formed compact object embedded in a region of active stellar birth. Everything about the environment pointed toward an energetic, youthful source. And yet, silence followed. Here is why that silence matters so much. CHIME had been unknowingly monitoring the location of RBFLOAT every single day for 7 years before the burst occurred. The telescope sees the entire northern sky once per day as Earth rotates beneath its fixed cylindrical reflectors. During those 7 years of daily monitoring, not a single prior burst was detected from that position. After the burst, continued monitoring has found nothing further. RBFLOAT appears to be a genuinely one-off event, a single scream from deep space followed by permanent quiet. This behavior is completely different from the famous repeating fast radio bursts that have defined much of the field's early progress, and it forces a confrontation with one of the most important unresolved questions in the field. Are one-off bursts and repeating bursts produced by the same kind of object in different circumstances, or do they represent fundamentally different phenomena that merely happen to look similar in a radio telescope? The repeating fast radio bursts present their own category of bewilderment. The first source confirmed to repeat was FRB 2012 1102A, localized in 2017 to a small dwarf galaxy roughly 3 billion light-years away. This source has emitted hundreds of detected bursts over the years, with activity that comes in clusters separated by periods of relative quiet. During active phases, dozens of bursts can arrive within hours. The individual bursts show complex internal structure, with multiple subpulses drifting downward in frequency over time, in a pattern astronomers call the sad trombone effect because of its resemblance to a descending musical note. The Faraday rotation measure of this source, which quantifies how much the polarization of the radio waves has been twisted by magnetic fields along the line of sight, is enormous and highly variable. This implies the burst source is embedded in an environment with intense dynamic magnetic fields, exactly the kind of environment expected near a young magnetar surrounded by the remnants of the supernova that created it. The sad trombone effect deserves a closer look because it is one of the few repeatable internal features of fast radio bursts that offers direct physical constraints on. The emission mechanism. When a repeating source produces a burst, the burst often contains multiple subpulses arriving in quick succession within the overall millisecond envelope. Each successive subpulse peaks at a slightly lower frequency than the one before it. Plot these subpulses on a graph of frequency versus time, and you see a distinctive downward drift, a staircase descending from high frequency to low frequency over the span of a few milliseconds. This pattern appears consistently in repeating fast radio bursts, but is largely absent from apparently non-repeating events, which is one of the strongest morphological differences between the two populations. The physical interpretation of this downward drift remains debated, but the leading models suggest it arises from the geometry of the emission region. If the burst is produced by a disturbance propagating outward through a magnetar's magnetosphere, different parts of the magnetosphere emit at different characteristic frequencies depending on their distance from the stellar surface. Regions closer to the star, where magnetic field lines are more tightly curved and particle densities are higher, emit at higher frequencies. Regions farther out emit at lower frequencies. As the disturbance moves outward, it lights up successively lower frequency zones, producing the characteristic downward sweep. This interpretation connects the subburst structure directly to the spatial extent and magnetic geometry of the emission region, which means the sad trombone is not just a curiosity, it is a probe of conditions within a few hundred kilometers of a neutron star's surface, a region so compact and so extreme that no other observational technique can access it. But if FRB 2012-1102A seemed to fit a magnetar narrative, the next major repeater complicated things considerably. FRB 2020-1124A, detected by CHIME and then monitored intensively by the FAST telescope in China, produced an extraordinary burst storm in 2021. Over a span of roughly 54 days, FAST recorded nearly 2,000 individual bursts from this single source. The burst rate was overwhelming, sometimes exceeding dozens per hour during peak activity. The Faraday rotation measure was unstable, shifting dramatically over timescales of days in ways that suggested the magnetic environment near the source was in constant upheaval. Some bursts were highly polarized, others showed almost no polarization. The spectral properties shifted from burst to burst in ways that no single model could neatly predict. The host galaxy turned out to be a massive barred spiral, completely unlike the small dwarf galaxy hosting FRB 2012-1102A. The source was located not in a dense star-forming core, but in a region with moderate stellar activity. The environment did not obviously scream young magnetar. It did not obviously scream anything. It simply produced a torrent of bursts with properties that changed almost as fast as astronomers could record them. Then came a repeater that introduced an entirely new dimension to the mystery. FRB 2018-09, 16b, discovered by CHIME in 2019, does something that no other fast radio burst source had been definitively shown to do before. It follows a schedule, not a rough tendency to cluster bursts at certain times, but a genuine periodic activity cycle with a measured period of approximately 16.35 days. For roughly 4 to 5 days out of every 16-day cycle, the source is active, producing detectable bursts. For the remaining 11 to 12 days, it falls silent. This pattern has held through years of monitoring with remarkable consistency. The bursts do not arrive at perfectly regular intervals within the active window. Their timing within those 4 or 5 active days appears random, but the window itself opens and closes on a clock that has not deviated significantly since the periodicity was first identified. The 16-day cycle of FRB 2018-09, 16b, immediately raised the question of what physical mechanism could impose such a rhythm on a fast radio burst source. A rotating neutron star cannot explain it. Even the slowest known pulsars rotate on timescales of seconds, not weeks. A free precession of the neutron star, a slow wobble in its rotation axis, could in principle produce a periodic modulation of the burst activity if the radio emission beam only sweeps past Earth during certain phases of the precession. But the required precession period of 16 days is at the extreme edge of what theoretical models predict for neutron stars, and the sharp transitions between active and silent phases are difficult to reproduce with a smoothly varying precession. a more widely discussed explanation involves a binary orbit. If the magnetar producing the bursts orbits a companion star with a 16-day period, the companion could periodically obscure the emission or alter the conditions in the magnetar's environment in ways that either permit or suppress burst activity. During portions of the orbit where the magnetar is unobstructed and its magnetospheric conditions are favourable, bursts escape and reach our telescopes. During other portions, a dense stellar wind or disk of material from the companion blocks or absorbs the radio emission. This model has the advantage of naturally producing sharp on-off transitions because an orbiting companion sweeps through distinct geometric configurations as it moves along its orbital path. It also connects to the broader theme that compact objects in binary systems may behave very differently from isolated compact objects, producing signals that reflect the dynamics of the binary interaction rather than the properties of the neutron star alone. But the binary explanation introduces its own complications. CHIME observations of FRB 2018-09, 16b have revealed that the bursts within the active window show a chromatic dependence, meaning the precise timing of the activity window shifts slightly depending on which radio frequency band is being observed. Higher frequency bursts tend to arrive at slightly different phases within the 16-day cycle compared to lower frequency bursts. This chromatic behavior is not easily explained by a simple geometric occultation from a binary companion and suggests that the periodicity may be linked to something more complex, perhaps a periodic variation in the plasma environment surrounding the source that affects different frequencies differently as the emission propagates outward. The chromatic periodicity adds another layer to a puzzle that was already deeply layered, and it has prompted some researchers to revisit precession models with more sophisticated treatments of how the emission beam interacts with the surrounding plasma. The contrast between RBFLOAT and these prolific repeaters highlights a deeper problem. If you lined up the properties of every known fast radio burst on a spectrum, from quiet one-off events to hyperactive repeaters with periodic modulation, the distribution would not show two neat clusters. It would show a messy continuum with blurry boundaries and awkward overlaps. Machine learning algorithms applied to the CHIME data have tried to impose order on this chaos. Using supervised classification methods trained on known repeaters and known non-repeaters, these algorithms can correctly identify most repeaters based on burst morphology alone. Repeating bursts tend to be broader in time and narrower in bandwidth. They show more complex substructure. Their spectral energy distributions differ subtly but measurably from one-off events. But the algorithms also flag a troubling number of apparently non-repeating bursts as likely hidden repeaters, sources that look morphologically like repeaters but have only been caught once. 6 sources classified as non-repeaters in the first CHIME catalogue were later confirmed as repeaters when subsequent bursts arrived during extended monitoring. How many more are out there, repeating at intervals too long or at energies too faint for current surveys to catch? This classification uncertainty is not merely academic. It determines how scientists model the population. If all fast radio bursts fundamentally come from the same type of object, perhaps magnetars at different stages of life, then the repeating and non-repeating distinction dissolves into an observational selection effect. Young, active magnetars repeat frequently enough for us to notice. Older, quieter magnetars repeat so rarely that we catch only one burst and never hear from them again. Under this interpretation, RBFLOAT might be a magnetar that exhausted some reservoir of energy in one spectacular outburst and then went dormant. But the alternative hypothesis is equally plausible. Perhaps one-off bursts and repeating bursts come from genuinely different physical channels. One-off events might result from catastrophic processes, a neutron star collision, a magnetic field reconfiguration so violent it can only happen once, or some other terminal event. Repeaters might involve a sustained engine, a magnetar that periodically releases energy through crustal fractures or magnetospheric instabilities over years or decades. And the periodic repeaters like FRB 2018-09 16b might represent yet a third category, sources where binary dynamics modulate the burst output on timescales determined by orbital mechanics, rather than the internal physics of the compact object. The data do not yet clearly favour one interpretation over the other, and this ambiguity sits at the heart of the field's unresolved tension. While fast radio bursts dominate the headlines, they are not the only class of mysterious deep space signal that has emerged in recent years. A separate and equally puzzling category has been quietly accumulating since 2022, and these signals are strange enough to have forced astronomers to question assumptions that have been secure for half a century. They are called long-period radio transients, and they operate on timescales that should be physically impossible for any known type of radio-emitting compact object. Conventional pulsars, the rotating neutron stars discovered in 1967, produce radio pulses with periods ranging from milliseconds to a few seconds. The mechanism is well understood. A neutron star spins. Its magnetic poles are offset from its rotational axis. Beams of radio emission emanate from those poles and sweep across space like lighthouse beams. Each time a beam crosses our line of sight, we detect a pulse. The period of the pulses equals the rotation period of the star. Pulsars slow down over time as they radiate energy away, and theory predicts that once a pulsar slows below a certain rotational threshold, roughly 10 to 20 seconds per rotation, its magnetic field can no longer sustain the particle acceleration needed to generate radio emission. The pulsar crosses what astronomers call the death line and goes radio silent. This framework has been remarkably successful. Every known pulsar until recently fit within its predictions. Then, in 2022, a team using the Murchison Wide Field Array in Western Australia discovered a radio source that pulsed once every 18 minutes. 18 minutes is hundreds of times slower than the slowest known pulsar. No neutron star should be able to produce radio emission while rotating that slowly. The source appeared, pulsed regularly for a few months, and then vanished. The discovery was stunning, but its transient nature left room for doubt. Perhaps the 18-minute source was a fluke, a short-lived phenomenon that would not be seen again. Perhaps it was an exotic but temporary state of some otherwise normal object, briefly switching on radio emission before returning to silence. The vanishing act made it difficult to study further and left the theoretical implications uncertain. That uncertainty was obliterated by the next discovery. In 2023, a team led by Natasha Hurley-Walker at Curtin University announced the detection of a source catalogued as GPMJ183910, a radio transient pulsing once every 21 minutes. But this source did something the 18-minute transient could not. It refused to disappear. Follow-up observations confirmed that GPMJ183910 was actively pulsing during the observation campaigns, producing regular radio bursts roughly every 21 minutes, with a pulse width of approximately 30 to 60 seconds per cycle. More remarkably, when the team searched archival data from the Very Large Array and the Giant Metrowave Radio Telescope, they found that this source had been detectable in observations dating back over 30 years. This was not a brief flare-up. This was a persistent radio emitter that had been pulsing for at least 3 decades, possibly much longer, sitting far below the conventional death line for radio pulsars, and apparently unconcerned with the theoretical rules that said it should have gone silent long ago. The persistence of GPMJ183910 is what makes it so devastating to the standard pulsar framework. The 18-minute source discovered in 2022 could be explained away as a temporary activation, perhaps a magnetar experiencing a brief episode of unusual activity before returning to quiescence. But an object that has been producing coherent radio pulses for 30 years at a rotation period of 21 minutes cannot be dismissed as a transient anomaly. It is a stable, persistent radio emitter operating at a period where no known neutron star should be able to generate radio light. Either the death line does not apply under certain conditions that current theory has not accounted for, or the source is not a neutron star at all, but some other class of object that produces radio emission through an entirely different mechanism. Both possibilities carry profound implications. If the death line is not absolute, then the theoretical understanding of how pulsars generate their radio emission needs revision at a fundamental level. If the source is not a neutron star, then a new category of radio-emitting compact object exists that was not predicted and is not yet identified. It was followed by additional discoveries of sources pulsing on timescales of minutes to hours, some repeated with extraordinary regularity. Others appeared briefly and then dropped below detection. The category was given the name long-period radio transients, and as of mid-2026, approximately a dozen are known. Their properties are unlike anything in the existing taxonomy of radio-emitting objects. One of the most striking examples is AY-SCAP J1424, discovered during the evolutionary map of the universe survey using the Australian Square Kilometre Array Pathfinder. During a long observing run on January 9, 2025, researchers detected 17 pulses spaced approximately 36 minutes apart, corresponding to a period of roughly 2,147 seconds. Follow-up observations confirmed the same timing across 8 consecutive days. Then the source dropped below the detection threshold and has not been seen since. The signal displayed polarization consistent with nearly 100% across the pulse profile, meaning the radio waves were extraordinarily well-ordered rather than scrambled. This degree of polarization implies a highly organized magnetic field geometry in the emitting region. Whatever produced these pulses was not random. It was structured, precise, and operating on a clock that no known isolated neutron star should be able to maintain while still generating radio light. The leading hypotheses for long-period radio transients have evolved rapidly. Initially, some researchers proposed that these sources might be ultra-slowly rotating magnetars, neutron stars with magnetic fields so powerful that they could somehow sustain radio emission even at rotation periods far beyond the conventional death line. This explanation requires exotic physics but is not entirely ruled out. Other researchers pointed to white dwarfs, the dense remnants of lower-mass stars, as potential sources. White dwarfs can have strong magnetic fields and rotate slowly, but they have never been observed to produce the kind of coherent, pulsed radio emission seen from long-period transients. A third and increasingly favoured hypothesis involves binary systems. A white dwarf in a close orbit with a low-mass companion star, typically a red dwarf, could interact magnetically with its partner in ways that produce periodic radio bursts, timed to the orbital period rather than the spin period of either star. In January 2026, a paper published in Nature Astronomy by Xanad Horvath and colleagues proposed a detailed binary model for long-period radio transients. The model suggests that magnetic interactions between a white dwarf and its companion star can channel energy into coherent radio emission when geometric conditions align during each orbit. The orbital period of the binary provides the clock, the magnetic interaction provides the energy, and the specific alignment conditions explain why the emission can appear and disappear over days or weeks as the system's orientation slowly changes relative to our line of sight. The model makes testable predictions, including specific relationships between pulse duration, polarization properties, and orbital parameters that can be checked against future observations. This binary hypothesis received a dramatic boost from a separate discovery. Gleam-XJ070437, identified by the same Murchison Wide Field Array team and followed up with the Meerkat telescope in South Africa, was traced not to an isolated neutron star but to a red dwarf star. With a period of 2.9 hours, it is the slowest long-period radio transient found so far. The localization to a specific stellar system was a breakthrough because it offered the first concrete anchor point for identifying what kind of object produces these signals. Red dwarfs are the most common stars in the Milky Way, making up approximately 70% of all stars, yet they are so intrinsically faint that not a single one is visible to the naked eye. If long-period transients are produced by interactions between white dwarfs and red dwarfs in binary systems, the potential population of sources is enormous, and the handful discovered so far would represent the tip of a vast observational iceberg. But even with the binary model gaining traction, 10 of the 12 known long-period radio transients remain without confirmed source identifications. Their positions have not been localized with enough precision to identify a specific stellar system, or no obvious counterpart exists at the identified position. These unidentified sources could be binaries consistent with the model, or they could be something else entirely. The diversity within the small-known sample is already larger than a single explanation comfortably accommodates. Some long-period transients pulse for months and then vanish. Others appear briefly, pulse for days, and disappear. GPM J183910 has been pulsing for more than 30 years. Some show smooth, clean pulse profiles. Others display complex substructure within each pulse. The polarization properties vary from source to source. The timescales range from minutes to hours. If all long-period transients are binaries, the binary configurations involved must span a wide range of orbital separations, magnetic field strengths, and companion types to account for this diversity. If some are not binaries, then additional source classes remain to be discovered. What connects fast radio bursts and long-period radio transients is not their physical mechanism, which likely differs profoundly between the two categories, but their shared status as signals that arrive before their explanations. Both classes were discovered through wide-field radio surveys that were designed to look for something else. Fast radio bursts were found in pulsar survey data. Long-period transients were found in continuum emission surveys. In both cases, the telescope detected something unexpected, a signal that did not match any predicted category, and the field has spent years since trying to reverse engineer what could produce it. This is the scientific process operating at the frontier. Detection outpaces theory. Instruments reveal phenomena that models did not anticipate, and the gap between the clarity of the signal and the murkiness of the explanation becomes a productive tension that drives new observations, new models, and eventually new understanding. But it is important to be precise about what remains unresolved and why it matters. The mystery of fast radio bursts is not that scientists have no idea what they are. The leading candidate, magnetars, has strong observational support. The mystery is that the magnetar explanation does not cleanly account for every observed property, every host environment, or every pattern of activity. Some bursts look like they come from magnetars. Others look like they might, but the evidence is ambiguous. A few look like they probably do not. The classification is incomplete. The physical mechanism converting magnetic energy into coherent radio emission is debated. Multiple competing models exist, each successful at explaining some observations and unsuccessful at explaining others. Similarly, the mystery of long-period radio transients is not that they come from nowhere. White dwarf binaries now have compelling evidence in at least one case. Isolated neutron stars with unusual properties remain a possibility for others. The mystery is that fewer than a dozen sources are known, most lack identified counterparts, and the range of observed properties already exceeds what any single model can comfortably explain. The classification is provisional. The sample is tiny, and every new discovery has the potential to either validate the emerging framework or break it. This is what makes deep space signals so scientifically valuable and so resistant to clean narrative resolution. They are not vague. They are not ambiguous noise. Fast radio bursts arrive with precise dispersion measures, measurable polarization, quantifiable energies, and localizable positions. Long-period transients repeat with clockwork regularity and display ordered polarization properties. These signals contain enormous amounts of physical information. The problem is not a lack of data. The problem is that the data point toward physical regimes where existing models reach their limits, where compact objects behave in ways that are technically permissible under known physics but have never been observed before, and where the diversity of behavior suggests multiple source populations overlapping in observational parameter space. The signals are not noise, they are structured, they are repeatable, at least some of them, they are energetic, and they are arriving at a rate that accelerates with every new telescope that comes online. The universe is not being coy. It is broadcasting vigorously and clearly. The challenge is not hearing the broadcast. The challenge is that the broadcast comes from engines so extreme, so compact, and so violently energetic that our current theoretical machinery cannot yet fully reconstruct what is happening inside them from the signal alone. And that challenge deepens considerably when you examine the specific objects most likely responsible for these emissions, because even the candidates we think we understand turn out to be far stranger than their textbook descriptions suggest. On April 28, 2020, a magnetar inside the Milky Way did something that had never been observed before. SGR 1935 plus 2154, a neutron star roughly 30,000 light-years from Earth, in the constellation Vulpecula, emitted a burst of radio waves so bright and so brief that it matched the profile of the fast radio bursts arriving from galaxies billions of light years away. Within milliseconds of that radio flash, multiple X-ray observatories in orbit around Earth detected a simultaneous burst of high-energy radiation from the same object. For the first time, a fast radio burst had been caught in the act of being produced by a known source. The culprit was a magnetar, one of the most extreme objects in the observable universe, and that single detection, confirmed independently by the CHIME telescope and the STARE-2 array in the United States, transformed the field overnight. But in the years since, the magnetar connection has proven to be not the answer to the fast radio burst mystery, but the beginning of a much stranger set of questions. A magnetar is a neutron star with a magnetic field so powerful it defies conventional intuition. Ordinary neutron stars already possess magnetic fields millions of times stronger than anything achievable on Earth. Magnetars take this to another level entirely. Their surface fields reach approximately 10 to the power of 15 Gauss, a quadrillion times the strength of Earth's magnetic field and roughly 1,000 times stronger than a typical neutron star. These magnetic fields are so intense that at a distance of halfway between Earth and the Moon, a magnetar's field would erase every credit card on the planet and fatally disrupt the biochemistry of every living cell. The energy stored in these fields is colossal, sufficient to power bursts of radiation that briefly outshine entire galaxies, and the fields are unstable. They twist, reconfigure, and occasionally snap like overstressed cables, releasing their stored energy in violent outbursts that span the electromagnetic spectrum from radio waves to gamma rays. SGR 1935 plus 2154 had been known to astronomers for years before its historic radio burst. Discovered in 2014, it had produced dozens of X-ray bursts characteristic of magnetar activity, short flashes of high-energy radiation powered by sudden releases of magnetic energy near the stellar surface. These X-ray bursts are relatively common among the roughly 30 known magnetars in our galaxy. What was unprecedented was the simultaneous production of a radio burst with properties matching extragalactic fast radio bursts. The radio burst, designated FRB 2020-04-28, lasted roughly half a millisecond and carried enough energy to be detectable at much greater distances, though it was still thousands of times weaker than the typical fast radio bursts arriving from other galaxies. That energy gap is itself a puzzle. If magnetars produce fast radio bursts, why was the galactic example so much fainter than its extragalactic counterparts? Either the Milky Way magnetar was producing a relatively modest burst by fast radio burst standards, or the extragalactic sources involve magnetars under far more extreme conditions, perhaps younger, more highly magnetized, or embedded in amplifying environments that boost the radio output. The years since 2020 have added complexity without delivering clarity. SGR 1935 plus 2154 has been monitored relentlessly by nearly every major X-ray and radio observatory available. It produced another fast radio burst-like event in October 2022, designated FRB 2022-1014A, again accompanied by X-ray activity. Detailed timing analysis revealed that this burst occurred between two spin-up glitches, sudden tiny increases in the neutron star's rotation rate caused by internal structural adjustments. The temporal coincidence between glitches, X-ray outbursts, and radio emissions suggests that all three phenomena are connected through changes in the magnetar's magnetosphere, the region of magnetized plasma surrounding the star, but the specific chain of events linking a glitch to a radio burst remains unclear. High-cadence observations with the NISA and NuSTAR X-ray telescopes during the 2022 outburst revealed rapid spectral evolution in the persistent X-ray emission, indicating that the magnetosphere was undergoing significant structural changes on timescales of hours. The burst spectra shifted in ways consistent with alterations in the geometry of the emitting region, yet not every X-ray burst produced a detectable radio counterpart. Some X-ray bursts arrived with no radio emission at all. This selective association implies that radio emission requires specific magnetospheric conditions beyond simply having a burst of X-ray activity. Something additional must align. Some geometric or energetic threshold must be crossed for the radio channel to activate. A 2026 study using the GCAM satellite added another layer. Researchers reported a detailed analysis of a particularly bright and unusual X-ray burst from SGRJ 1935 plus 2154 that was temporally associated with a fast radio burst. The X-ray burst showed a complex light curve that could be described by a fast-rise exponential decay function overlaid with several narrow spikes. Most intriguingly, the team identified a possible quasi-periodic oscillation feature at approximately 18 Hz within the burst. Quasi-periodic oscillations, or QPOs, in magnetar bursts are significant because they can encode information about the physical structure of the neutron star itself. An 18 Hz oscillation could correspond to seismic vibrations in the star's crust, ripples propagating through the ultra-dense matter after a sudden structural fracture. If confirmed, this would support models in which fast radio bursts are triggered by starquakes, sudden cracking events in the crystalline crust of the neutron star that release magnetic energy and launch disturbances through the magnetosphere. The analogy to earthquakes is not merely poetic. A 2024 study published in Monthly Notices of the Royal Astronomical Society found that the statistical time correlations of repeating radio pulses from this same magnetar closely resemble the aftershock patterns of terrestrial earthquakes, following similar power law clustering in time and energy. The neutron star's surface may literally be quaking, and each quake may trigger a cascade of radio emission detectable across cosmic distances. To understand why a starquake on a neutron star can release more energy in a millisecond than anything achievable on Earth, you need to understand what the interior of these objects actually contains, because a neutron star is not a uniform ball of matter. It is a layered structure with distinct physical regimes stacked from the surface inward, each more extreme than the last. The outermost layer is a solid crust roughly 1 to 2 kilometers thick, composed of a crystalline lattice of iron nuclei arranged in a rigid grid interspersed with a sea of free electrons. This crust is extraordinarily strong. The material is compressed to densities of roughly 1 billion kilograms per cubic centimeter, millions of times denser than the densest material on Earth. Beneath this outer crust lies the inner crust, where conditions become genuinely alien. The nuclei in this region are so tightly packed that neutrons begin to drip out of the nuclei entirely, forming a superfluid neutron gas that flows between and around the remaining nuclear clusters. The matter here exists in phases that have no analogue in terrestrial physics, including exotic configurations sometimes called nuclear pasta, because the nuclei are stretched and deformed by the intense pressure into shapes resembling sheets, tubes, and tangled filaments. Beneath the inner crust lies the outer core, a vast region composed almost entirely of superfluid neutrons, with a small admixture of superconducting protons and electrons. This material flows without friction and conducts electricity without resistance, properties that profoundly influence how the star's magnetic field is anchored and how it evolves over time. At the very center sits the inner core, where densities exceed anything replicable in any particle accelerator on Earth. What exists at these densities remains genuinely uncertain. It could be hyperons, baryons containing strange quarks. It could be free quarks and gluons in a state called quark-gluon plasma. It could be something else entirely that current nuclear physics cannot predict. The inner core of a neutron star is one of the few places in the universe where the fundamental nature of matter under extreme compression remains an open question. When a starquake occurs, the crystalline lattice of the outer crust fractures under the stress of the evolving magnetic field. The energy released by this fracture depends on the rigidity of the lattice, the depth of the crack, and the amount of magnetic energy that the fracture allows to escape. Because the crust material is compressed to such extraordinary densities, even a tiny fracture releases energy that dwarfs any terrestrial seismic event. A crack propagating through a few hundred meters of neutron star crust can release as much energy as the total output of a moderate star over hours. That energy launches disturbances into the magnetosphere above, where the extreme magnetic fields can convert it into coherent radio emission through mechanisms like the monster shocks described earlier. The starquake model thus connects the internal structure of the neutron star directly to the observable properties of the fast radio burst, making the burst a seismological probe of an object whose interior cannot be studied by any other means. But even this compelling picture leaves enormous gaps. Starquake models can explain why individual Bajan bursts are brief and why they cluster in time, but they struggle to account for the extraordinary luminosity of extragalactic fast radio bursts, which outshine the galactic magnetar burst by factors of thousands or more. Something about the most powerful fast radio bursts requires either much more violent starquakes than anything observed locally, or an entirely different amplification mechanism that boosts the radio output far beyond what a simple crustal fracture can produce. Theoretical work has pursued both directions. In February 2026, a study published in Physical Review Letters explored a mechanism called monster shocks. These are extreme plasma acceleration events that occur when fast magnetosonic waves collide within the complex magnetic geometry of a magnetar's magnetosphere. The researchers modelled how these shocks form in realistic three-dimensional configurations, rather than the simplified geometries used in earlier work. They found that monster shocks can convert magnetic energy into coherent radio emission with extraordinary efficiency, and that the predicted emission frequencies match observations with remarkable precision. For SGR 1935 plus 2154 specifically, the predicted radio frequency of approximately 1.4 GHz falls squarely within the range detected by the STARE-2 instrument. Monster shocks offer a physically grounded mechanism for producing intense coherent radio emission from magnetar magnetospheres, but the model has not yet been tested against the full diversity of fast radio burst properties, and it remains one candidate mechanism among several. This is the central frustration of the magnetar hypothesis. The evidence linking magnetars to fast radio bursts is strong, but incomplete. One galactic magnetar has produced confirmed fast radio burst-like emission. The properties of that emission, its coherence, its millisecond timescale, its simultaneous X-ray association, are consistent with what magnetar models predict. But extrapolating from one local example to the thousands of extragalactic fast radio bursts in the CHIME catalogue requires assumptions that the data do not yet fully support. The extragalactic bursts span an enormous range of energies, repetition patterns, and host environments. Attributing all of them to magnetars demands that magnetars themselves exhibit a far wider range of behaviors than the handful of galactic examples have demonstrated. And some of the host environments in which fast radio bursts have been localized do not easily fit the magnetar story at all. Consider the host galaxy problem. If fast radio bursts come from young magnetars born in core collapse supernovae, they should overwhelmingly appear in galaxies with active star formation and should cluster in regions where massive stars are being born and dying. Many do. RBFLOAT was localized to a star-forming spiral arm, FRB 2012-1102. A resides in a star-forming dwarf galaxy. But other fast radio bursts have been traced to the outskirts of massive galaxies with low star formation rates, to elliptical galaxies dominated by old stellar populations, and even to environments consistent with globular clusters, ancient collections of stars billions of years old, where no recent supernovae should have occurred. These discrepant localizations suggest that not every fast radio burst comes from a young magnetar. Some may involve older compact objects, perhaps neutron stars that acquired extreme magnetic fields through binary interactions late in life, or white dwarf systems that produce fast radio burst-like emission through mechanisms entirely different from the magnetar channel. The host galaxy diversity is not easily swept under a single theoretical rug. The single most challenging localization for the young magnetar model came with FRB 2020-01, 20E, a repeating fast radio burst that was traced to a globular cluster associated with the galaxy M81, located approximately 12 million light-years from Earth. Globular clusters are among the oldest stellar structures in the universe. They are dense spherical collections of hundreds of thousands of ancient stars, typically 10 to 13 billion years old, bound together by mutual gravity. They contain no gas clouds, no young massive stars, and no recent supernova remnants. The stars in globular clusters exhausted their capacity to produce supernovae billions of years ago, Every massive star that was going to explode already did so in the distant past. If fast radio bursts require young magnetars born from fresh supernovae, then a globular cluster is the last place you would expect to find one. Yet there it was, repeating, clearly localized, and stubbornly inconsistent with the standard narrative. The discovery of FRB 2020-01-20E forced theorists to consider alternative formation channels for magnetar-strength magnetic fields. In the dense stellar environments of globular clusters, close encounters between stars and compact objects are far more common than in the general galactic population. Neutron stars that were born billions of years ago with ordinary magnetic fields could, in principle, have their fields amplified through interactions with binary companions or through accretion of material from nearby stars. Some models propose that the merger of two white dwarfs within a globular cluster could produce a new neutron star with a freshly generated ultra-strong magnetic field, effectively creating a magnetar through a pathway that does not involve a core collapse supernova. Other models suggest that the burst might not come from a magnetar at all, but from some other compact object whose emission mimics a fast radio burst without involving the extreme magnetic fields characteristic of magnetars. The globular cluster source remains one of the most important constraints on fast radio burst progenitor models, precisely because it rules out the simplest version of the young magnetar hypothesis. Whatever produces fast radio bursts in globular clusters must have formed through a channel available in ancient dense stellar environments where conventional supernovae no longer occur. Gamma-ray bursts offer a parallel case study in classification difficulty. For decades, the taxonomy of gamma-ray bursts seemed clean. Short-duration bursts lasting less than 2 seconds came from neutron star mergers. Long-duration bursts lasting more than 2 seconds came from the collapse of massive stars into black holes. This classification was supported by host galaxy associations, afterglow properties, and, in the case of the landmark 2017 event, simultaneous gravitational wave detection, confirming a neutron star merger as the source of a short gamma-ray burst. Then GRB 211211A arrived and broke the framework. Detected by the Fermi Gamma-Ray Space Telescope in December 2021, this burst lasted over a minute, firmly placing it in the long-duration category. But its afterglow properties, its host galaxy environment in the constellation Bo-OTs, and its light curve evolution all pointed not toward a massive star collapse, but toward a compact binary merger. Visible light follow-up revealed no supernova, which should have been present if a massive star had died. Instead, the fading light showed characteristics of a kilonova, the radioactive glow produced when neutron-rich material ejected during a merger synthesizes heavy elements. Some researchers proposed the burst resulted from a collision between a neutron star and a white dwarf, a merger channel that had been theorized but never observationally confirmed. Others suggested a neutron-star merger that somehow produced an unusually long-lived jet. The event demonstrated that the neat two-category classification of gamma-ray bursts was insufficient. Nature had found a way to produce long-duration high-energy emission from a source that should only produce short bursts according to the existing taxonomy. The lesson from gamma-ray bursts applies directly to fast radio bursts and long-period radio transients. Classification systems built on a limited sample of observations inevitably fail when new data reveals the full diversity of nature's repertoire. The repeater versus non-repeater distinction in fast radio bursts may be as fragile as the short versus long distinction in gamma-ray bursts. The magnetar versus white dwarf binary debate for long-period transients may eventually give way to a recognition that multiple source populations coexist within the same observational category. The signals themselves do not carry labels identifying their origin. They carry physical information, energies, timescales, polarization properties, dispersion measures, and spectral structures that must be painstakingly decoded through comparison with theoretical models. When multiple models can explain the same signal with different assumptions, the classification remains provisional, no matter how confident any individual research team might sound. The role of environment in shaping these signals is increasingly recognized as critical and poorly understood. A magnetar embedded in a dense supernova remnant surrounded by highly magnetized plasma will produce radio emission with different propagation characteristics than the same magnetar in a cleaner environment. Faraday rotation measures, which track how the polarization of radio waves is twisted by intervening magnetic fields, vary enormously from source to source. Some repeating fast radio bursts show Faraday rotation measures that change by hundreds of units over weeks, implying that the magnetic environment near the source is evolving rapidly. Others show stable Faraday rotation, suggesting a more quiescent surrounding medium. These environmental differences affect not just the observed properties of the signal, but potentially the emission mechanism itself. The most dramatic demonstration of environmental influence came from the burst storm of FRB 2020-11-24A during its 2021 active phase. The FAST telescope's intensive monitoring campaign captured not just nearly 2,000 bursts, but also the most detailed Faraday rotation evolution ever recorded from any fast radio burst source. Over the course of roughly 54 days, the rotation measure swung wildly, shifting by hundreds of units in ways that could not be explained by changes in the distant intervening medium between the source galaxy and Earth. The changes had to be local, occurring in the immediate environment of the burst source itself. Some researchers interpreted the rotation measure variations as evidence that the magnetar sits in a binary system with a companion star whose stellar wind reshapes the local magnetic environment on timescales of days. As the companion moves along its orbit, the density and magnetic structure of its wind varies relative to the line of sight between the magnetar and our telescopes. When the wind is dense and strongly magnetized along our sightline, the Faraday rotation measure climbs. When the wind shifts or thins, the measure drops. This interpretation would make FRB 2020-11-24A another example of a binary system influencing burst properties, connecting it to the binary themes already emerging from long-period radio transients and the periodic fast radio burst, FRB 2018-09-16B. But the binary interpretation of the rotation measure evolution is not the only one on the table. Alternative models propose that the fluctuations could result from the magnetar itself reshaping its own local environment. Powerful magnetar outbursts can eject plasma into the surrounding space, creating a dynamic magnetized nebula whose properties change rapidly as new material is ejected and older material expands outward. Under this scenario, the rotation measure variations would not require a binary companion at all. They would simply reflect the magnetar's own violent output, modifying the medium through which its subsequent bursts must propagate. Distinguishing between these scenarios requires long-term monitoring at multiple wavelengths. If a binary companion exists, its influence should produce periodic or quasi-periodic patterns in the rotation measure tied to the orbital cycle. If the magnetar itself is responsible, the variations should correlate with burst activity rather than with any external clock. The data from the 2021 storm show suggestive but not definitive patterns, and the source has been quieter since, limiting opportunities for further analysis. The environmental question remains open, and its resolution would fundamentally change how astronomers interpret not just this one source, but the entire population of repeating fast radio bursts, whose Faraday rotation measures show significant variability. A magnetar interacting with a dense wind from a companion star might produce bursts through a different channel than an isolated magnetar experiencing crustal fractures. The same underlying object could look completely different depending on its surroundings, and disentangling the intrinsic source properties from the environmental imprint is one of the most technically challenging aspects of the field. Neutron star mergers add yet another dimension. The 2017 detection of gravitational waves from a binary neutron star merger, followed by a short gamma-ray burst and a kilonova, confirmed that merging neutron stars produce multi-messenger signals spanning the electromagnetic spectrum and gravitational wave frequencies. That event, detected by the LYEGO and Virgo gravitational wave observatories and observed by dozens of electromagnetic telescopes around the world, remains the only neutron star merger so far detected through both gravitational waves and light simultaneously. It confirmed long-standing theoretical predictions about how merging neutron stars forge heavy elements and produce relativistic jets. But it also raised questions about what happens in the moments immediately before the final collision. During the last few orbits, when the two neutron stars are spiraling toward each other at a significant fraction of the speed of light, with their magnetospheres violently entangled. New simulations published in 2025, performed on NASA supercomputers, modeled the complex magnetospheric interactions between neutron stars in those final orbits with unprecedented detail. The research, led by Dimitrios Skiathas at NASA's Goddard Space Flight Center, tracked how the magnetic field lines of two approaching neutron stars twist, reconnect, and snap as the stars complete their last several orbits. The simulations showed that the tangled magnetic fields undergo rapid and dramatic changes during this phase, producing electromagnetic precursor signals, bursts of high-energy radiation emitted before the stars actually make contact. These precursor signals are brief, energetic, and potentially detectable by wide-field gamma-ray and X-ray observatories if the merger occurs close enough, and if instruments happen to be observing in the right direction at the right time. The critical question for fast radio burst science is whether these pre-merger electromagnetic precursors could include coherent radio emission. If the violent magnetic reconnection events in the final orbits convert sufficient energy into coherent radio waves, the resulting signal could in principle resemble a fast radio burst. The timescales would be right, on the order of milliseconds. The energies could be right, depending on the magnetic field strengths of the merging neutron stars, and the coherent emission mechanism, driven by extreme plasma acceleration in rapidly reconfiguring magnetic geometries, would parallel the monster shock mechanism already proposed for magnetar bursts. No such precursor has been definitively detected from a confirmed neutron star merger, but the theoretical prediction creates a tantalizing possibility. If even a small fraction of fast radio bursts come from the moments just before neutron star mergers, they would represent signals from events that are about to produce gravitational waves. Detecting a fast radio burst followed seconds or minutes later by a gravitational wave chirp from the same sky position would be one of the most extraordinary multi-messenger discoveries in the history of astrophysics, linking two entirely different observational frontiers through a single cataclysmic event. The prospect of detecting pre-merger radio emission has practical implications for gravitational wave astronomy as well. Current gravitational wave detectors like LYEGO and Virgo can detect neutron star mergers out to distances of several 100 million light-years, but they cannot predict when or where a merger will occur. The detection happens after the fact, when the gravitational wave signal arrives. If a fast radio burst serves as a precursor, arriving seconds before the merger, it could provide an early warning that allows gravitational wave detectors to optimize their sensitivity in the relevant sky direction and electromagnetic telescopes to begin observing immediately rather than scrambling after the gravitational wave alert. This would transform the multi-messenger observation of neutron star mergers from a reactive pursuit into a proactive one. The possibility of multiple progenitor channels is not a weakness of the field. It is a reflection of the diversity of extreme compact objects and environments that the universe contains. Magnetars with different ages, field strengths, and surrounding environments. White dwarf binaries with different orbital configurations and companion masses. Neutron star mergers at different stages of inspiral. Ancient neutron stars in globular clusters that somehow acquired extreme magnetic fields through pathways that bypassed conventional supernovae. Exotic objects that may not yet have been individually identified. Each of these could produce coherent radio emission under the right circumstances, and the fast radio burst catalogue may be sampling all of them simultaneously, without yet having the tools to reliably sort one from another. The classification problem is not a sign of failure. It is a sign that the observational window has been flung open wider than the theoretical framework can currently accommodate. What emerges from all of this is a picture that is richer, more complicated, and more honest than any single headline can capture. The universe's most extreme compact objects produce signals that are detectable across cosmic distances. Those signals carry physical information about the sources and their environments. Astronomers can now detect these signals at a rate of several per day and localize many of them to specific galaxies and even specific regions within those galaxies. The leading source candidates, magnetars and exotic binaries, have strong observational support. But the full physical mechanism of emission, the reason for the staggering diversity of burst properties, the question of how many distinct progenitor channels contribute to the observed population, and the precise conditions that determine whether a given object will produce a fast radio burst or remain radio silent remain genuinely open questions. Knowing the likely source category does not close the investigation. It opens it further, because even within the category of magnetars, the range of observed behaviors is so wide that no single model accounts for all of them. The same class of object can whisper or scream, repeat endlessly or fire once and fall silent, emit in radio and X-ray simultaneously or in radio alone, depending on conditions that theory has not yet mapped completely. This is what it means for a signal to resist clean interpretation. Not that science is lost, not that the universe is unknowable, but that the objects producing these signals operate in physical regimes so extreme that our models, built from observations of calmer and more familiar systems, reach their limits. The magnetic fields are stronger than anything we can replicate in a laboratory by factors of billions. The densities exceed anything found on Earth by factors of trillions. The energy releases happen on timescales shorter than a single beat of a human heart. These are not conditions where textbook physics can be confidently applied without extension, modification, or entirely new theoretical development. The signals are telling us exactly what the sources are doing. The challenge is building a theoretical language fluent enough to translate what the signals are saying. And that challenge, far from being a dead end, is what makes this one of the most active and rapidly evolving frontiers in all of astrophysics. But stepping back from the individual signals and their candidate sources raises a broader and more unsettling question. What does it mean that the universe's most powerful objects routinely announce themselves through emissions we can detect long before we can fully explain them? And what does that pattern reveal about the nature of scientific understanding itself? On June 1st, 2026, a team of astronomers published a study in Nature Astronomy describing a discovery they called a cosmic Rosetta Stone. The source was AY-SCAP J1745, a long-period radio transient that had been pulsing with metronomic regularity from a position near the center of our galaxy. But unlike nearly every other long-period transient discovered in recent years, this one did not remain anonymous. Through a combination of radio observations with the Australian Square Kilometre Array Pathfinder, X-ray monitoring with orbiting observatories, and optical follow-up with ground-based telescopes, the team identified exactly what was producing the signal. A white dwarf, the dense remnant of a dead star roughly the size of Earth but with the mass of our Sun, was actively pulling material from a companion red dwarf star in a close binary orbit. The two stars circle each other once every 1.3 hours, and with each orbit, the magnetic interaction between the accreting white dwarf and the infalling material produces both radio bursts and X-ray flashes, repeating precisely on the orbital clock. The radio bursts from this system are more than 100 times more powerful than any previously observed from an accreting white dwarf binary, and they display a distinctive signal pattern that had previously been detected in only one other context in the entire universe: the electromagnetic interaction between Jupiter and its volcanic moon Io. A mechanism first identified in our own solar system turns out to operate at vastly amplified scales in a stellar graveyard thousands of light years away. This discovery is extraordinary for what it confirms, and equally extraordinary for what it leaves unresolved. AY-SCAP J 1745 is the first long-period radio transient with a fully identified multi-wavelength source, meaning researchers can now see the object that produces the signal across radio, X-ray, and optical wavelengths simultaneously. This makes it a decoder ring for the entire class of signals. By comparing the known properties of this confirmed binary system with the observed properties of other long-period transients whose sources remain unidentified, astronomers can begin testing whether those other sources are also binaries, or whether something fundamentally different is responsible. The Rosetta Stone analogy is apt. Just as the original Rosetta Stone allowed scholars to translate Egyptian hieroglyphics by providing the same text in a known language, AY-SCAP J1745 provides a known physical system whose signal properties can be compared against the cryptic emissions of its unidentified cousins. But here is the critical caveat that the discovery team themselves emphasized. Even with this breakthrough, 10 of the 12 known long-period radio transients remain without confirmed source identifications. AY-SCAP J1745 proves that white dwarf binaries can produce long-period radio transient signals. It does not prove that all long-period transients come from white dwarf binaries. The known sample is so small and so diverse in pulse timing, duration, polarization, and activity patterns that multiple source populations could easily coexist within this single observational category. Some might be binaries, others might be isolated neutron stars with anomalous magnetic properties. Still others might involve objects or interactions that have not yet been theorized. A Rosetta Stone is invaluable, but it does not translate every language. It translates one. This pattern, where a major discovery resolves part of a mystery while simultaneously revealing how much remains unresolved, is not a peculiarity of long-period radio transients. It is the defining rhythm of deep space signal science as a whole. Every breakthrough in the field over the past 2 decades has followed the same arc. A signal is detected that does not fit existing categories. Intense observational effort narrows down the source. A candidate explanation emerges with strong but incomplete evidence, and the explanation, rather than closing the case, opens new questions that the original discovery could not have anticipated. Fast radio bursts followed this arc from the Lorimer Burst in 2007 through the magnetar connection in 2020 to the localization of RBFLOAT in 2025. At each stage, the field advanced enormously. At each stage, the advance revealed that the remaining unknowns were deeper and more intricate than previously suspected. The reason this pattern persists is not that scientists are doing something wrong. It is that the objects producing these signals exist in physical regimes where simple explanations are structurally insufficient. A magnetar is not a simple object. It is a sphere of matter roughly 20 kilometers across, compressed to densities exceeding 1 billion tons per teaspoon, with a crystalline crust floating on a sea of superfluid neutrons, wrapped in magnetic field lines carrying more energy than the entire luminous output of the Milky Way. The physics operating inside this object involves general relativity, quantum chromodynamics, plasma physics, and solid-state mechanics simultaneously, under conditions that cannot be replicated in any laboratory on Earth. When such an object fractures its crust, reconfigures its magnetic field, and launches a coherent burst of radio emission across the cosmos in less than a millisecond, the signal carries information about all of these physical regimes encoded together. Unpacking that information requires theoretical tools that are still being forged. The signal is clear, the translation is not. This gap between detection and explanation deserves careful examination because it challenges a widespread assumption about how science progresses. The popular narrative suggests that detection and explanation happen in quick succession. A signal is found, scientists identify the source, the mystery is solved. The textbook is updated, move on, but the actual history of astrophysics tells a very different story. Pulsars were detected in 1967 by Jocelyn Bell Burnell and initially labelled LGM1 for Little Green Men, because no natural explanation seemed adequate at the time. The identification of pulsars as rotating neutron stars followed within months, which seems rapid until you consider that neutron stars had been theorized in 1934, more than 3 decades before their signals were detected. The theoretical framework was waiting. The signal simply confirmed it. Gamma-ray bursts followed a far slower path. First detected in the late 1960s by Vela military satellites, their cosmological origin was not confirmed until the late 1990s, a gap of roughly 3 decades. The identification of short gamma-ray bursts with neutron star mergers came even later, confirmed by gravitational wave observations only in 2017, half a century after the first detection. The signals were clear from day one. The explanation took 50 years. Fast radio bursts are currently somewhere in the middle of this timeline. First detected in 2007, linked to magnetars in 2020, localized with precision in 2025, but still lacking a unified emission mechanism or a complete census of progenitor types. The pace of discovery is faster than it was for gamma-ray bursts, driven by instruments like CHIME that detect multiple bursts per day rather than a handful per year. But the diversity of observed properties suggests that a complete understanding may require not one breakthrough but several, each resolving a different piece of the puzzle. The magnetar connection was a major piece. The identification of white dwarf binaries as sources of long-period transients is another. More pieces are needed, and the shape of the final picture remains genuinely uncertain. What makes this uncertainty scientifically productive, rather than merely frustrating, is that the signals themselves are already useful even before their origins are fully explained. Fast radio bursts have become tools for probing the large-scale structure of the universe, and the story of how they achieved this status is itself one of the most remarkable developments in recent cosmology. The problem they solved had been nagging astronomers for decades. Standard cosmological models, grounded in observations of the cosmic microwave background, and confirmed by measurements of the primordial abundances of light elements, predict a specific total amount of ordinary baryonic matter in the universe. Baryonic matter means the familiar stuff: protons, neutrons, electrons, the atoms that make up stars, planets, gas clouds, and human beings. The prediction is precise. Baryonic matter should constitute roughly 5% of the measured content of the universe. But when astronomers added up all the baryonic matter they could actually see in stars, in galaxies, in the hot gas-filling galaxy clusters, the total came up short. Badly short. Only about half the predicted baryonic matter could be accounted for. The rest was missing. Not dark matter, which is a separate category entirely. Not dark energy. Ordinary atoms that cosmological theory insisted must exist, but that no telescope could find. Theorists had long predicted where these missing baryons should be hiding. Computer simulations of cosmic structure formation showed that most of the universe's ordinary matter should reside not inside galaxies, but between them, in the vast filaments of the cosmic web connecting galaxy clusters across hundreds of millions of light-years. This intergalactic material, known as the warm-hot intergalactic medium, was predicted to have temperatures between 100,000 and 10 million degrees, hot enough to be almost fully ionized but too diffuse and too cool to show up brightly in X-ray observations. It existed in a detection blind spot, too hot for radio telescopes tuned to cold neutral hydrogen, too cool and thin for X-ray telescopes designed to see the blazing gas inside galaxy clusters. The missing baryons were predicted to be everywhere, filling the cosmic web in a thin fog of ionized hydrogen and helium that was tantalizingly close to undetectable. Fast radio bursts provided the breakthrough. Every burst that travels from a distant galaxy to Earth passes through whatever ionized material lies between its source and our telescope. That material slows the lower frequency components of the radio pulse slightly more than the higher frequency components, producing the characteristic dispersion that has been central to fast radio burst science since the Lorimer Burst. The total dispersion measure of a burst records the integrated column of free electrons along the entire line of sight. If you know how far away the burst came from, and you know how much dispersion was contributed by the Milky Way and by the host galaxy, then whatever dispersion remains must come from the intergalactic medium. Measure enough bursts at known distances, and you can weigh the intergalactic medium directly. This is precisely what a landmark 2020 study accomplished. The research, often associated with the late astronomer Jean-Pierre Mouquart, and sometimes called the Mouquart relation, used a sample of localized fast radio bursts with measured distances to their host galaxies. By comparing each burst's dispersion measure to its distance, the team demonstrated a clear linear relationship. More distant bursts showed proportionally higher dispersion, exactly as predicted. If the intergalactic medium contains the missing baryonic matter at the density cosmological models require, the result was striking in its clarity. The missing baryons were not missing at all. They were exactly where theory predicted, spread through the cosmic web in a diffuse, ionized fog. Fast radio bursts, by passing through this fog on their way to Earth, had effectively weighed it. A phenomenon whose own origin remained mysterious had solved one of the longest-standing problems in observational cosmology. The elegance of this result lies in what it does and does not require. It requires knowing the distances to the host galaxies, which comes from redshift measurements made by optical telescopes. It requires measuring the dispersion of each burst, which comes from the radio data itself. It requires subtracting the contribution of our own galaxy and the host galaxy to the total dispersion, which involves models that carry some uncertainty but are increasingly well constrained. What it does not require is knowing what produced the burst. The cosmological measurement depends entirely on how the signal propagates through the universe, not on how the signal was generated. The emission mechanism could be magnetar starquakes, monster shocks, binary interactions, or something not yet imagined. The Merquart relation works regardless. Fast radio bursts are also being explored as independent probes of the Hubble constant, the rate at which the universe expands. By combining dispersion measures with redshift measurements of host galaxies, researchers can constrain the relationship between distance and intervening electron density in ways that depend on cosmological parameters. A 2025 study using 64 localized extragalactic fast radio bursts demonstrated that the technique produces Hubble constant estimates with smaller error bars than some previous methods. The bursts do not yet resolve the ongoing tension between different measurements of the expansion rate, but they offer a completely independent line of evidence drawn from a phenomenon that did not exist as a research tool 15 years ago. Signals whose origin remains debated are nonetheless producing cosmological measurements of genuine scientific value. And as the catalogue of localized bursts grows from dozens to hundreds to thousands over the coming years, the precision of these measurements will improve dramatically, potentially offering a decisive test of whether the Hubble tension reflects new physics or systematic measurement errors. This is a concept worth pausing on, because it overturns a common intuition about how knowledge works. We tend to assume that a phenomenon must be fully understood before it can be useful. You need to know what a thing is before you can use it as a tool. But fast radio bursts demonstrate the opposite. Their utility as cosmological probes does not depend on knowing what produces them. It depends on understanding how their signals propagate through the cosmos, which is a separate and better understood problem. The emission mechanism is mysterious. The propagation physics is well constrained. The signal can be used as a measuring instrument, even while the instrument's own internal workings remain partly opaque. This is not unprecedented in the history of science. Physicians used aspirin for decades before understanding the biochemical mechanism by which it reduced pain and inflammation. Engineers used steel long before the atomic scale physics of iron-carbon crystal structures was fully characterized. Utility and understanding are related but separable. Fast radio bursts are useful now. Their full explanation will come later. Both facts can be true simultaneously. The philosophical weight of this observation extends beyond fast radio bursts to the entire enterprise of deep space signal science. The universe is not silent. It is saturated with electromagnetic emissions spanning every wavelength from radio to gamma rays. Most of these emissions come from sources that are well understood. Stars emit thermal radiation, hot gas, in galaxy clusters, emits X-rays. Synchrotron radiation from charged particles spiraling in magnetic fields fills the radio sky. These signals are thoroughly catalogued, well modelled, and theoretically accounted for. But at the edges of this well-understood landscape, where conditions become most extreme, signals emerge that resist clean categorization. Fast radio bursts from objects whose emission mechanism is debated, long-period radio transients from sources that defy conventional pulsar physics, gamma-ray bursts that blur the boundaries between established categories, quasi-periodic eruptions from galactic centers that may involve stars being partially consumed by black holes on repeating orbits. Each of these signal classes occupies a frontier where detection has outpaced explanation, where instruments can record the phenomenon with precision, but theories cannot yet fully reconstruct the physics that produced it. This frontier is not static. It moves. Every decade, phenomena that were once mysterious become understood, and new mysteries take their place. Pulsars were frontier science in the 1970s. Gamma-ray bursts were frontier science in the 1990s. Gravitational waves were frontier science in the 2010s. Fast radio bursts and long-period radio transients are frontier science now, in the mid-2020s. The pattern is consistent. The universe reveals its most extreme inhabitants through signals first. The signals are always clearer than the explanations, and the explanations, when they finally come, typically reveal that the objects responsible are stranger and more diverse than the initial models predicted. There is something deeply humbling about this pattern, and it touches on what it means to exist as a conscious species in a universe that operates on scales and under conditions so far removed from everyday experience that our evolved intuitions offer no guidance. Human beings developed the capacity for abstract thought on the savannas of East Africa, solving problems related to food, shelter, predators, and social groups. Nothing in that evolutionary history prepared us to think about objects 20 kilometers across with magnetic fields a quadrillion times stronger than our planets, releasing more energy in a millisecond than a star produces in days, from distances so vast that the light carrying the signal has been travelling since before our species existed. We build the instruments, we record the data, we construct mathematical models that approximate the physics, but the intuitive understanding, the gut-level comprehension that we bring to problems involving rocks, rivers, and human-scale forces does not apply. The universe at its most extreme is not merely large or old or energetic. It is alien in the deepest sense, operating under rules that are technically part of the same physics we use on Earth, but producing outcomes that no human mind could have predicted from first principles alone. And yet, we do make progress. That is perhaps the most remarkable fact of all. Despite the cognitive mismatch between human intuition and cosmic extremes, the scientific method works. It works not because individual scientists are smarter than the problems they face, but because the method itself is designed to compensate for human limitations. Hypotheses are tested against data. Models are discarded when they fail to predict observations. Competing explanations are evaluated based on evidence rather than elegance or preference. The process is slow, often frustratingly so, and it frequently produces intermediate states of understanding where partial answers coexist with deep uncertainties. Fast radio burst science is in exactly such an intermediate state right now. Magnetars are probably involved. White dwarf binaries are probably involved. Multiple progenitor channels probably exist. The emission mechanism probably involves coherent radiation processes in extreme magnetic environments. None of these probabilities has been elevated to certainty. All of them are supported by evidence. The field is not confused. It is honestly reporting the state of knowledge at a frontier where the data have outrun the models. The instruments that will push this frontier forward over the coming decade are already being built or are already operational. The Chime Outrigger array will continue localizing fast radio bursts with arc-second precision, building a catalogue of host galaxies and source environments, large enough to test whether the population is truly diverse or converges on a smaller number of progenitor types. The FAST telescope in China, the most sensitive single-dish radio telescope in the world, will continue monitoring repeating fast radio bursts with enough sensitivity to detect the faintest bursts in their activity cycles. The Deep Synoptic Array will add localization capability in the southern sky. And then there is the instrument that may ultimately transform the field more than any other. The Square Kilometre Array, known as the SKA, is currently under construction across 2 continents, with low-frequency antenna stations spread across the remote deserts of Western Australia and mid-frequency dish arrays scattered across South Africa and several partner countries in Africa. When completed, the SKA will be the largest and most sensitive radio telescope ever built, with a total collecting area approaching 1 square kilometre. Its sensitivity will exceed that of any existing radio telescope by an order of magnitude, meaning it will detect fast radio bursts that are currently too faint for any instrument to catch. More critically, the SKA is designed from the ground up for simultaneous detection and localization. Unlike current systems where detection and precise localization require separate instruments or time-consuming follow-up, the SKA will pinpoint the position of each fast radio burst at the moment of detection, automatically and in real time. This means every detected burst will come with an immediate host galaxy identification, eliminating the bottleneck that currently limits the field. The catalogue of localized fast radio bursts, which currently numbers in the dozens, could grow to tens of thousands within a few years of the SKA reaching full operation. At that scale, statistical patterns that are currently invisible will emerge. The question of whether repeating and non-repeating bursts come from genuinely different progenitor populations will be answerable through sheer weight of numbers. The relationship between burst properties and host environments will be mapped with enough precision to test every competing model. and entirely new classes of radio transient phenomena, too faint or too infrequent for current surveys to detect, will almost certainly appear in the data, continuing the pattern of instruments revealing what theories did not predict. Together, these observatories will transform the relationship between detection and explanation, replacing educated guesses about source populations with statistically grounded answers derived from samples large enough to reveal what small catalogues conceal. The conclusion of this story is not a resolution. It is a recognition. Deep space signals are mysterious, not because science has failed, but because the universe's most extreme objects and environments announce themselves through patterns of radiation that arrive at our instruments long before the full physical explanation can follow. This has been true for every category of extreme astrophysical phenomenon ever discovered. Pulsars announce neutron stars. Gamma-ray bursts announce neutron star mergers and black hole births. Gravitational waves announce the dynamics of space-time itself. In every case, the signal came first. The understanding came later, sometimes decades later. Fast radio bursts and long-period radio transients are the latest frontier in this ongoing process of discovery. They represent signals from compact objects operating under the most extreme conditions the universe can create. Conditions where magnetic fields, gravitational forces, and plasma dynamics intersect in ways that strain the limits of theoretical physics. The signals are precise, they are energetic, they are structured, they repeat or they do not, for reasons that remain actively debated. And they are arriving at our telescopes faster than we can explain them, building a catalogue of cosmic emissions that contains more information than our current models can fully decode. This is not a crisis of ignorance. It is the natural state of a science that has built instruments powerful enough to detect phenomena at the very edge of what physics can describe. The real shock is not that strange signals exist in deep space. Strange signals have always existed. The real shock is that some of the universe's most extreme and most revealing phenomena still reach us first and only as unresolved emissions. Patterns of energy that we can record with extraordinary fidelity but cannot yet trace back to a single, clean physical story. The cosmos does not wait for our readiness. It broadcasts on its own schedule, in its own language, from engines we are still learning to name. Every millisecond flash from a magnetar in a distant galaxy, every clockwork pulse from an anonymous binary near the galactic center, every silent gap where a signal should repeat but does not, carries information about the most violent and most compact objects in existence. We are listening, we are cataloguing, we are building better instruments and better models with every passing year. But the universe, as always, is several steps ahead. The signals have arrived, the full translation is still being written, and the frontier between what we can detect and what we can explain remains one of the most productive, most humbling, and most thrilling boundaries in all of science.